Welcome to our exploration of igneous rocks and volcanic activity. Igneous rocks, whose name comes from the Latin word igneous, meaning fire, are formed through the cooling and solidification of magma or lava. This process can happen either deep underground or at the Earth's surface, leading to a fascinating variety of rock types and textures. In this video, we'll break down how igneous rocks form, the difference between intrusive and extrusive rocks, and how these processes connect to volcanic activity. By understanding the basics, we set the stage for a deeper dive into the textures, compositions, and geological significance of these fiery rocks. Let's start by looking at the rock cycle and how igneous rocks fit into the bigger picture of Earth's dynamic crust. Igneous rocks form in two main ways, from lava that cools quickly at the surface or from magma that cools slowly deep underground. When lava erupts and solidifies on the surface, it forms extrusive or volcanic rocks, which typically have small crystals due to rapid cooling, a texture known as a phanitic. Basalt is a classic example. Contrast, when magma cools slowly underground, it creates intrusive or plutonic rocks with large visible crystals known as phaneritic texture. Granite is a well-known example. Sometimes rocks experience two-stage cooling, resulting in a porphyritic texture with both large and small crystals. The cooling rate directly influences the rock's appearance and structure, making texture a key clue to a rock's history. Let's look at some images to see these differences in action. Mineral composition of igneous rocks is largely determined by the chemistry and temperature of the magma from which they crystallize. Most igneous rocks are rich in silicate minerals, but the specific types depend on formation conditions. Light-colored, felsic rocks like granite are high in feldspar and silica, while dark-colored, mafic rocks like gabbro are rich in magnesium and iron. Owen's reaction series helps us predict which minerals will form as magma cools, showing a progression from simple to complex silicates and from calcium-rich to sodium-rich feldspars. This series is a powerful tool for geologists, revealing how different rock types can form from the same original magma, simply by cooling at different rates or temperatures. Understanding these concepts helps us interpret the diversity of igneous rocks found on Earth. Magma forms deep within the Earth through three main processes: increasing temperature, decreasing pressure, decompression, melting, or adding water and other volatiles. These processes are closely tied to plate tectonics. For example, decompression melting occurs at divergent boundaries and hotspots where mantle material rises and pressure drops. Adding water, on the other hand, is common at subduction zones, where oceanic plates sink and release water into the overlying mantle, lowering its melting point. These mechanisms explain why volcanic activity is concentrated along plate boundaries and hotspots. Understanding how and where magma forms not only helps us predict volcanic eruptions, but also reveals the dynamic nature of our planet's interior. Intrusive igneous bodies come in various shapes and sizes, each with unique characteristics. Plutons are masses of igneous rock that crystallize deep within the crust, while batholiths are vast collections of plutons covering large areas. Dikes and sills are flat bodies that cut through or follow rock layers, respectively, and laccoliths are mushroom-shaped intrusions that push overlying layers upward. These structures are not only important for understanding Earth's geology, but also have practical implications. Intrusive rocks are generally strong and resistant, making them excellent for construction and engineering projects. However, their tendency to form fractures can present challenges. Recognizing these features helps engineers and geologists make informed decisions about land use and hazard assessment.